The cosmos beckons with its countless mysteries, challenging our understanding and igniting our imagination. From the mysterious depths of black holes to the enigmatic behavior of distant galaxies, the cosmos abounds with phenomena that defy simple explanation. Join us as we unravel the secrets of the universe, one cosmic mystery at a time. Beneath the thick and poisonous clouds of Venus lies an incredibly hostile environment, far from favorable to any form of life as we know it. Venus's atmosphere is composed mostly of carbon dioxide, and clouds of sulfuric acid cover the planet in a shroud. These clouds create such a strong greenhouse effect that the average surface temperature is about 800 degrees Fahrenheit, making it hotter than Mercury's surface despite being farther from the Sun. Atmospheric pressure on Venus is another major factor contributing to its inhospitable nature. At the surface, the pressure is about 90 times Earth's pressure, which is akin to being nearly a mile under the ocean. The immense pressure is capable of crushing any human-made spacecraft, making exploration extraordinarily difficult. The combination of extreme temperature and high pressure creates conditions that no known organism on Earth can survive. In addition, there is volcanic activity on the surface of Venus, which accounts for the harsh landscape. Scientists believe that many of these volcanoes may still be active, releasing additional gases and contributing to the thickness of the planet's atmosphere. The presence of volcanic plains and vast elevations adds to Venus's intrigue, revealing a planet shaped by powerful geologic forces. In recent years, scientists have even speculated about the possibility of microbial life in the upper atmosphere, where conditions are slightly less extreme. However, the harsh conditions on the surface, combined with clouds of sulfuric acid, make Venus virtually unsuitable for life of any complex form. The mysteries hidden beneath its clouds continue to mesmerize researchers, which has prompted further missions to explore this enigmatic planet. The idea of a ninth planet lurking in remote corners of our solar system has gained traction among astronomers in recent years, primarily due to the unusual orbits of some celestial objects in the Kuiper belt. Distant icy bodies exert a gravitational influence, suggesting the presence of an unseen giant planet. This hypothetical planet is often referred to as Planet 9 or sometimes Planet X, although no direct observations of it have yet been made. Planet 9 is believed to be much larger than Earth, perhaps several times its mass, and has a highly elliptical orbit that puts it well beyond the known planets. According to some models, it could be anywhere from 20 to 800 astronomical units away from the Sun, where 1 astronomical unit is the average distance from Earth to the Sun. This vast distance makes detecting a planet extremely challenging, as it may be relatively dim and distant, but its gravitational influence may be enough to affect the orbits of debris in the Kuiper belt. Interestingly, the search for the ninth planet has been the subject of considerable research and debate. Astronomers are using modern telescopes and computer modeling to study the potential location of this elusive planet. As data accumulates, researchers hope to pinpoint its location and eventually obtain a direct image of the ninth planet, which could shed light on our understanding of the formation and evolution of the solar system. Unraveling the mystery of the ninth planet may also spark discussions about the possibility of other undiscovered planets lurking in the far corners of our solar system. The dynamics of distant celestial objects hint at a rich and complex structure with many mysteries still waiting to be discovered. As new observations are made, the search for this mysterious planet continues to inspire scientists and astronomy enthusiasts alike. The hexagonal storm at Saturn's North Pole is one of the most intriguing and unique weather phenomena observed in our solar system. This striking hexagonal pattern, about 14,000 miles wide, has fascinated scientists since it was first discovered by the Voyager spacecraft in the 1980s. The stable shape of this massive storm raises questions about the complex dynamics of Saturn's atmosphere. The hexagon is believed to be the result of a complex interaction of atmospheric currents rather than a single storm. It is formed by the interaction of fast-moving winds in Saturn's atmosphere that create a standing wave pattern. Cold winds in Saturn's polar region blow at speeds of more than 150 miles per hour. These winds create a rotational effect combined with the planet's rapid rotation, resulting in a distinct geometric hexagonal shape. Researchers have used fluid dynamics experiments to reproduce this hexagonal structure in a laboratory setting. When they create a rotating system of fluids and introduce an obstacle into the flow, a hexagonal pattern emerges. This suggests that the hexagon on Saturn is stabilized by the hydrodynamics underlying the planet's atmosphere. Seasonal changes also play a role, as fluctuations in sunlight and temperature affect wind patterns and can change the appearance or intensity of a hexagonal storm. The hexagon is not just static. It exhibits change and dynamics by showing the formation and movement of small storms along its edges. Remarkably, it has persisted for decades, if not longer, indicating a robust atmospheric system that continues to intrigue scientists. Understanding the hexagonal storm not only reveals the complexity of Saturn's weather, but also deepens our knowledge of hydrodynamics on a planetary scale. Uranus is unique among the planets in our solar system due to its sharp tilt, which causes it to spin on its side. While most planets have an axial tilt of less than 30 degrees relative to their orbits around the Sun, Uranus boasts an inclination of about 98 degrees. This peculiar orientation sets it apart from others and produces a distinct set of seasonal patterns and atmospheric behavior. The leading theory for Uranus's unusual tilt suggests a massive collision with one or more celestial bodies during its formative years. Such a significant impact could have knocked the planet off its original axis, resulting in the extreme tilt observed today. This theory is consistent with the notion that major collisions were common in the early solar system, which could easily alter the planet's rotation axes. In addition to its axial tilt, Uranus's rotation is also remarkable because it rotates very slowly around its axis, making one revolution in about 17 hours. As a result, at each pole, long periods of sunshine are followed by prolonged darkness, resulting in extreme seasonal variations. Uranus's orientation relative to its orbit allows one hemisphere to be constantly exposed to sunlight for long periods of time, while the other hemisphere remains in darkness. In addition, Uranus's unusual tilt affects the dynamics of its atmosphere. The planet's weather is characterized by high-velocity winds and shifting clouds, providing an intriguing insight into the planet's complex processes. Researchers continue to study Uranus, and the mysteries surrounding its tilt and rotation provide valuable clues about the formation of the planets and the turbulent history of our solar system. The origin of Mars's moons, Phobos and Deimos, has intrigued scientists for years, generating various theories about how these small celestial bodies came to orbit the red planet. Phobos, the larger of the two moons, and Deimos are irregularly shaped and relatively small compared to Earth's moons, 14 and 8 miles in diameter respectively. The unusual characteristics of these objects suggest to astronomers that they may not be native to Mars, but captured asteroids from the asteroid belt. The most widely supported hypothesis suggests that Phobos and Deimos are remnants of a larger population of rocky bodies in the asteroid belt. It is hypothesized that early in the history of the solar system, gravitational interactions may have drawn these objects to Mars, allowing them to become satellites of the planet. The close similarities between the composition of Phobos and certain types of asteroids, particularly carbonaceous chondrites, further supports this capture theory. Another compelling aspect in favor of their origin is the low density of both moons, indicating their composition is rich in carbonaceous materials and possibly ice. This matches the characteristics of some asteroids, hinting that Phobos and Deimos formed somewhere in the solar system before falling under the gravitational pull of Mars. Their irregular shape and the significant craters they display also suggest a collision history comparable to that of many other small bodies in the solar system. However, there are alternative theories, including the possibility that they formed in situ from debris ejected into Mars's orbit as a result of collisions with the planet itself. Despite the various hypotheses, the nature of Phobos and Deimos remains the subject of ongoing research. Future missions targeting these moons may yield new insights that could help shed light on the intriguing history of Mars and its unique satellites. Beneath Europa's thick icy crust lies one of the most compelling candidates for potential extraterrestrial life in our solar system. This moon of Jupiter is believed to possess a subsurface ocean hidden beneath an impressive layer of ice several miles thick. Scientists estimate that this ocean may contain more than twice as much water as Earth's, making Europa a particularly interesting object to study. The presence of liquid water is a critical factor in the search for extraterrestrial life. Water is often considered a universal solvent essential for biochemical processes. The ocean beneath Europa's icy surface is thought to be in contact with the Moon's rocky mantle, allowing chemical exchanges that could create a suitable environment for life. Just as hydrothermal vents on Earth give rise to diverse ecosystems, scientists hypothesize that similar processes may occur on Europa's seafloor, where mineral-rich water could nourish potential microbial life forms. Data from instruments such as Galileo and observations from the Hubble Space Telescope show plumes of water vapor erupting from Europa's surface. These plumes provide tantalizing clues about the composition of the subsurface ocean, hinting at the possibility of organic molecules. Analyzing these features could provide more information about the Moon's potential suitability for life without the need to drill for ice. Future missions, such as NASA's Europa Clipper, aim to study the Moon's icy crust and more thoroughly assess its potential for life. This research could unlock the secrets of Europa's hidden ocean and explore the conditions that may allow life to thrive in an environment vastly different from Earth's. The idea of detecting life beneath Europa's ice is fascinating to scientists and humanity, raising profound questions about our place in the universe. Mercury's composition is strikingly different from that of other terrestrial planets. Notably, the Moon has an unusually large iron core, comprising about 70% of the planet's total mass. This disproportionate presence of iron has puzzled scientists and led researchers to delve deeper into the formation of Mercury and the processes that shaped it in the early solar system. According to one prevailing theory, Mercury's large iron core is the result of a massive impact during its formation. During the formation of the planets in our solar system, there were numerous collisions of protoplanetary material. As a result of a violent collision, much of Mercury's outer silicate mantle may have been blown away, leaving behind much of the dense iron core. The remaining mantle is relatively thin compared to the mantles of other planets, emphasizing the dominant role of the core in Mercury's overall structure. Another factor contributing to Mercury's formation may be the planet's proximity to the Sun. As the closest planet, Mercury experienced higher temperatures during its formation, which may have affected the differentiation of materials. Under the action of heat, lighter compounds may have vaporized or been pushed outward, while denser ions subsided to form the core. This differentiation process may have been more extreme for Mercury than for other terrestrial planets such as Earth, Venus, and Mars. In addition, Mercury's evolution is also influenced by its geologic history. Traces of volcanic activity have been found on the planet, and it is speculated that it may have occurred after the core was formed. Understanding Mercury's current structure, including its core and mantle, gives us valuable clues about the formation of planets and the unique conditions that can lead to such distinctive characteristics of celestial bodies. As we learn more about Mercury through current and future missions, the enigmatic nature of its large iron core is becoming increasingly clear, deepening our understanding of the history of the solar system. The mysterious spokes observed in Saturn's rings are a fascinating feature that has puzzled scientists since it was first discovered in the 1980s by the Voyager spacecraft. These spokes appear as radial structures that can span thousands of kilometers and appear to change in intensity and shape over time. Their transient nature, combined with their striking appearance, makes them one of the most intriguing phenomena associated with Saturn's iconic rings. The prevailing theory for the formation of these spokes suggests that they result from the interaction of charged dust particles inside the rings and Saturn's magnetic field. The spokes are thought to be made up of small particles that are electrically charged by sunlight and interaction with the planet's magnetic field. The charging process causes particles to become suspended in the rings, resulting in visible features as they interact with various magnetic forces and gravitational influences. Observations have shown that these spokes tend to appear more clearly when Saturn is close to the equinox, the time when the Sun casts a shadow on the rings. This seasonal effect affects the brightness and visibility of the spokes, suggesting that they may be affected by changes in lighting conditions. When Saturn's rings are illuminated in a certain way, the charged particles can align or cluster together, creating the striking linear patterns we observe. Despite ongoing research, many aspects of spicules remain elusive, leading to various hypotheses about their formation and behavior. Some scientists speculate that the spokes may be related to the dynamics of the ring particles themselves or even the gravitational interaction of nearby moons. As new missions and improved observational techniques continue to yield data about Saturn and its rings, we will be able to better understand these fascinating and mysterious structures in one of the most fascinating systems in our solar system. The formation of Pluto and its largest moon, Charon, is a fascinating story that has intrigued scientists for decades. Both celestial bodies are in the Kuiper Belt, a region beyond Neptune inhabited by many small icy objects. The prevailing theory suggests that Pluto and Charon formed from the same primordial material as other bodies in the Kuiper Belt at the dawn of our solar system. According to this model, Pluto and Charon likely formed through a process called accretion. According to this scenario, dust and ice particles condensed in the cold outer regions of the solar system, gradually forming larger bodies. By colliding and interlocking with each other, these particles formed large planetesimals. Over time, gravity continued to cause these objects to collide and merge, leading to the formation of Pluto. This process would also have allowed smaller bodies to combine to form Charon, which is unusually large compared to Pluto, making it unique among the large moons of our solar system. However, the relationship between Pluto and Charon is particularly intriguing. The size ratio of the two planets, where Charon's diameter is about half that of Pluto, suggests that a significant collision occurred during their formation. Some scientists speculate that Charon may have formed after a massive collision knocked a significant amount of material off Pluto. This debris then merged into Charon, resulting in the synchronized relationship we see today. The two bodies are tidally locked to each other and always show the same face. Further studies of the Pluto-Charon system, including data obtained in 2015 by NASA's New Horizons spacecraft, have provided valuable insights into their composition and geology, revealing a complex history. Understanding their formation not only sheds light on the dynamics of the Kuiper Belt, but also provides a broader view of the processes that shape the solar system as a whole. Through ongoing research, we continue to learn about these distant worlds and the cosmic events that brought them into existence. Bright spots on the dwarf planet Ceres are one of the most intriguing features observed in our solar system. Ceres, located in the asteroid belt between Mars and Jupiter, has attracted the attention of scientists since NASA's Dawn spacecraft began its mission to study the dwarf planet in 2015. The brightest of these bright spots are located in an area called the Okator crater and have sparked much interest in their composition and origin. These bright spots are thought to be composed primarily of sodium carbonate, a type of salt, as well as other reflective materials. Brightness is likely due to how sunlight interacts with the surface, emphasizing how differently bright spots reflect light compared to the surrounding terrain. Spectroscopic analysis has revealed the presence of certain salts, suggesting that these materials may have originated from salt water beneath Ceres's surface. When liquid water rich in these salts rose up and evaporated, it left behind the bright remnants we observe. The presence of these bright spots indicates that cryovolcanism, or cold volcanism, may have occurred on Ceres in the past. This geologic process involves the eruption of icy materials rather than molten rock. The idea is that warm salt water may have penetrated through cracks in Ceres' crust, leading to the formation of the bright deposits. Continued study of these areas has revealed several features, such as domes and mounds, that may indicate past geologic activity. Understanding the bright spots on Ceres is important for several reasons. Not only do they provide insight into the dwarf planet's geologic history, but they also have implications for the broader study of icy bodies in our solar system. The presence of water, even in frozen or salty form, raises questions about the possibility of past habitability or the existence of life in such extreme conditions. While research continues, Ceres's bright spots remain the focus of researchers, revealing the complexity and richness of this intriguing celestial body. Inside the event horizon of a black hole is one of the most mysterious and extreme environments in the universe. The event horizon represents a boundary beyond which nothing can escape the formidable gravitational pull of a black hole, including light. Beyond this threshold, the concept of location and time undergoes profound changes due to the intense action of gravitational forces. It is believed that when anything crosses the event horizon, it is inexorably drawn toward the singularity, the core of a black hole, where density becomes infinite and the known laws of physics collapse. At this point, space and time lose their usual meanings. According to current theories, all paths, regardless of direction, eventually lead to the singularity, creating a one-way journey for anything that dares to approach it. This irreversibility is what defines the event horizon as the point of no return. The environment within the event horizon is also characterized by extreme tidal forces. Near the singularity, the gravitational attraction differs dramatically between the parts of the object closer to the center of the black hole and those farther away. This discrepancy can lead to a process known as spaghettization, where objects are stretched vertically and compressed horizontally, resembling strands of spaghetti. This effect occurs due to the curvature of spacetime caused by the enormous gravity of a black hole. Given the current state of physics and our understanding of black holes, much about what happens inside the event horizon remains speculative. As scientists continue to explore the interplay between general relativity and quantum mechanics, questions about the nature of spacetime, the conservation of information, and the fate of matter and energy subjected to these extreme conditions will remain relevant. The quest to understand black holes and what's inside them is not only a journey into the depths of these mysterious objects, but also a deep exploration of the fabric of the universe itself. The formation of supermassive black holes at the centers of galaxies is a complex process that remains an active area of research in astrophysics. These giants can reach masses millions or even billions of times that of our Sun, and their presence affects the dynamics and evolution of the galaxies in which they reside. Understanding how they are formed involves several interrelated theories. One of the leading hypotheses suggests that supermassive black holes are formed by the merger of smaller black holes and dense star clusters. In the early universe, the rapid collapse of massive clouds of gas and dust may have led to the formation of many small black holes. As these black holes drift through the surrounding matter, accreting gas in the process, some of them may eventually coalesce through gravitational interactions to form larger black holes over time. Another important factor is the role of the environment in which galaxies evolve. In the dense centers of galaxies, interactions between stars and gas clouds can lead to more efficient accretion of material onto these black holes. As they accumulate mass, they can emit enormous amounts of energy, which is often seen in the form of quasars, the incredibly bright and energetic centers of active galaxies. Intense luminosity occurs when gas spirals into a black hole, resulting in extremely high temperatures and radiation. The growth of supermassive black holes can also be linked to the overall evolution of galaxies. Mergers between galaxies, common throughout cosmic history, can involve gas and stars in the central regions, enhancing the growth of existing black holes. Such interactions not only increase their mass, but also determine the structure and dynamics of galaxies. The balance between the growth of black holes and the galactic environment plays an important role in the evolution of both. Despite these theories, many details about the formation of supermassive black holes remain unresolved. Research continues to investigate how these huge entities manage to form so quickly after the Big Bang, and how they interact with their host galaxies over cosmic time. Ongoing observations with modern telescopes are revealing more about the nature and formation processes of supermassive black holes and providing a deeper understanding of the interactions between black holes and the galaxies they inhabit. Fast radio bursts, known as FRBs, are high-energy and extremely short bursts of radio waves that have attracted the attention of astronomers and astrophysicists around the world. First detected in 2007, these mysterious signals last only a few milliseconds, but emit an astonishing amount of energy equivalent to what the Sun radiates for 10,000 years. Understanding their origin and mechanisms has become an important area of research in astrophysics. The exact cause of fast radio bursts remains unclear, leading to many theories about their origin. One well-known hypothesis suggests that FRBs may arise from extraordinary cosmic events such as neutron star collapse or neutron star mergers, when extreme gravitational and magnetic forces generate intense bursts of energy. Another possibility is the interaction of magnetars, highly magnetic and rapidly spinning neutron stars, with their environment. These magnetar bursts can produce powerful bursts of radiation that can potentially manifest as FRBs. Moreover, some of the more exotic theories suggest that FRBs may be related to processes in the early universe, such as the formation of black holes or even signals from advanced extraterrestrial civilizations. Although the latter idea is tantalizing, the scientific community has tended to focus on natural astrophysical phenomena as the sources of these radio bursts. Recent advances in observational technology have allowed astronomers to determine whether some FRBs belong to specific galaxies, providing clues to their origin. Notably, some FRBs are recurrent, suggesting that they are associated with localized, energetic astrophysical sources. The ongoing study of fast radio bursts continues to yield exciting discoveries, bringing us closer to understanding these elusive cosmic phenomena. While scientists work to unravel their mysteries, FRBs contribute to our knowledge of the universe and the many dynamic processes occurring beyond our planet. Magnetars are an interesting class of neutron stars known for their incredibly powerful magnetic fields, whose strength can exceed 1 trillion Gauss, making them the most magnetically powerful objects in the universe. The origin of these huge magnetic fields is rooted in the processes that occur during the formation of neutron stars, as well as the unique properties of their dense and compact matter. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, collapsing under its own gravity. The core can shrink into a neutron star, a remnant of the original stellar core where neutrons are packed tightly together by extreme gravitational forces. When a collapse occurs, several important factors contribute to the formation of an intense magnetic field. According to one leading theory, during the rapid rotation of a collapsing star, the conservation of angular momentum leads to a strengthening of the existing magnetic field. The dense matter of a neutron star, combined with the intense rotation and factors associated with a supernova explosion, can lead to a dynamo effect. As the star rotates, it generates a magnetic field, the strength of which can increase dramatically. Furthermore, the conditions inside a neutron star are extreme. At such high densities, matter behaves differently than under normal conditions, allowing for complex interactions that contribute to the generation of the magnetic field. The presence of superfluid neutrons and related phenomena can also affect the structure of the magnetic field. In a magnetar, these fields can occur rapidly, resulting in a core that can maintain and preserve an extremely strong magnetic field. In addition, the enormous energy associated with the magnetars can cause the magnetic field to gradually decay or rearrange over time. As they age, magnetars can periodically release bursts of energy or flares due to magnetic field reconfiguration, releasing vast amounts of energy and emitting radiation in multiple wavelength ranges. This unique behavior reveals not only the potential of magnetars, but also their complex evolution and interactions with their environment. Ongoing studies of these stellar phenomena allow us to better understand the physics behind their powerful magnetic fields and the implications of their study in the universe. Dark energy is the mysterious force that pervades the universe and is responsible for its accelerated expansion. Discovered in the late 20th century through observations of distant supernovae, scientists discovered that the universe is not only expanding, but doing so at an ever-increasing rate. This discovery has sparked increased interest and research into what dark energy actually is. About 70% of the universe is thought to be composed of dark energy. Despite the prevalence of this phenomenon, its exact nature remains elusive. One leading explanation states that dark energy is a property of space itself. As space expands, more and more dark energy appears, creating a feedback loop that contributes to further acceleration. This concept is rooted in Einstein's general theory of relativity, which allows for the existence of a cosmological constant, a term that can explain the density of energy in empty space. Alternative theories suggest that dark energy may be a dynamic field that changes over time, affecting acceleration at different epochs in cosmic history. Some scientists speculate that it may be related to changes in gravity on cosmic scales. Each of these theories attempts to reconcile the observations with our understanding of fundamental physics, but none has yet provided a definitive explanation for the phenomenon. The study of dark energy represents one of the major challenges of modern cosmology. Its discovery has raised more questions than answers, prompting scientists to develop new observational methods and theoretical models. Unraveling the secrets of dark energy may not only help us understand the fate of the universe, but also deepen our understanding of the fundamental laws governing cosmic evolution. Quasars are some of the brightest objects in the universe, often outshining entire galaxies. The huge release of energy results from activity around supermassive black holes located at the centers of distant galaxies. When matter is spiraled into black holes, it forms an accretion disk composed of gas, dust, and other materials that become incredibly hot due to friction and gravitational forces. This process converts potential energy into thermal energy, resulting in extraordinary levels of light and radiation. The temperature in an accretion disk can reach millions of degrees, causing the matter to emit powerful electromagnetic radiation across the entire spectrum, including visible light, ultraviolet radiation, and X-rays. The energy emitted by quasars can reach levels 1,000 times the energy of all the stars in a typical galaxy combined. It is because of this prohibitive brightness that quasars can be detected at great distances, allowing astronomers to observe them from billions of light-years away. Another contribution to the energy production in quasars comes from relativistic jets emitted along the black hole's axis of rotation. These jets are composed of charged particles that are accelerated to near the speed of light, releasing additional energy in the form of radiation. These jets can propagate over vast distances, sometimes thousands of light-years, and affect their host galaxies by transferring energy and momentum to surrounding matter. Studying quasars expands our understanding of the evolution of galaxies and the universe itself. By studying their properties, including their brightness and spectrum, astronomers gain insight into the conditions of the early universe and the processes that govern the formation and growth of black holes. Quasars serve as cosmic beacons, illuminating the depths of cosmic history and the complexity of the forces driving the evolution of the universe. Gamma-ray bursts are the most powerful explosions observed in the universe, releasing huge amounts of energy in the form of gamma rays, which are the most energetic form of light. These unusual phenomena are thought to occur during the death of massive stars, or when compact objects such as neutron stars or black holes merge. In the case of massive stars, when they exhaust their nuclear fuel, they can collapse under their own gravity, leading to a catastrophic implosion and subsequent supernova explosion. If a core collapse is accompanied by powerful jets of matter, these jets can produce the gamma rays that characterize the outburst. When a neutron star merges with another neutron star or black hole, it can also result in a gamma ray burst. In this scenario, the merger process releases enormous gravitational energy and can lead to the formation of a rapidly rotating black hole surrounded by an accretion disk. When matter is pulled into a black hole, powerful jets are ejected along its axis of rotation. If these jets are directed toward Earth, we observe them in the form of a gamma-ray burst. Gamma-ray bursts fall into two main categories: long-period bursts, lasting from a couple of seconds to several minutes, and short-period bursts, usually lasting less than 2 seconds. Long-duration bursts are mostly associated with the death of massive stars, while short-period bursts are usually associated with the merger of compact objects. This distinction helps scientists understand the different environments and conditions that lead to these explosive phenomena. The energy released in a gamma-ray burst can be staggering, often exceeding the total radiation from our Sun over its lifetime in just a few seconds. These bursts are so bright that they can be observed over vast cosmic distances, allowing astronomers to study these phenomena and gain insight into the extreme processes occurring in the universe. Understanding gamma-ray bursts not only sheds light on stellar evolution and black hole behavior, but also challenges our understanding of fundamental physics in the extreme. Binary star systems, consisting of two stars gravitationally bound together, often form from the same dense region of gas and dust in a molecular cloud. When parts of a cloud break apart under gravity, they can break up into smaller clumps, each of which begins the star formation process. If two such clumps are close enough, they eventually form stars orbiting each other. Initial conditions play a crucial role in determining the properties and evolution of a binary system. Once a binary system is formed, its evolution can take different paths depending on what happens. Their evolution can follow different paths depending on the masses of the stars and their orbital characteristics. If two stars have similar masses, they may simultaneously undergo similar stages of evolution, leading to complex interactions. As they evolve, they may expand and become red giants. If the stars are close enough, their outer layers can begin to transfer mass to each other, leading to phenomena such as mass exchange, or even the formation of additional structures such as accretion disks around the companion star. In cases where one of the stars becomes much more massive than the other, it may become a supernova, leaving behind a neutron star or black hole. A companion star will continue its evolution independently. At these moments, the dynamics of the system can change significantly, especially if the supernova remnants gravitationally interact with the companion star. This can often lead to scenarios such as the formation of a binary neutron star system, or a pair of neutron stars with a black hole, both of which can emit gravitational waves as they spiral towards each other. The study of binary star systems is essential to understanding stellar evolution and the mechanics of the universe. By observing these systems, astronomers can collect data on stellar masses, luminosities, and ages, contributing to broader models of how stars form, evolve, and ultimately affect their galactic environment. This study not only expands our knowledge of the life cycles of stars, but also informs theories about the distribution of matter in the universe. Cosmic rays are high-energy particles coming from space, and those with ultra-high energy are particularly intriguing to scientists. The energy of these cosmic rays can exceed 1 quintillion electron volts, which is millions of times more energetic than particles created in man-made gas pedals such as the Large Hadron Collider. The origin of these ultra-high-energy cosmic rays remains the subject of active research, with several potential sources being investigated. According to one leading hypothesis, ultra-high-energy cosmic rays emanate from supermassive black holes located at the centers of active galaxies. These regions contain vast amounts of energy and can accelerate protons and heavier nuclei to extreme speeds through processes such as shock waves and magnetic fields in the vicinity of a black hole. When charged particles travel through intergalactic space and interact with photons from the cosmic microwave background, they can reach energies far beyond what is currently achievable in the laboratory. Another suspected source of these high-energy particles are gamma-ray bursts, which are the most energetic events in the universe. During these explosive episodes, energy is concentrated in a very limited region capable of accelerating particles to ultra-high energies. In addition, certain types of supernova remnants and neutron star mergers are also considered potential sources because they can create the necessary conditions for particle acceleration. Although there are suspected sources, pinpointing the exact origin of ultra-high energy cosmic rays is difficult because of their trajectory. They are affected by the magnetic fields present in interstellar and intergalactic space. As a result, it can be almost impossible to trace their source. Advanced observational techniques using vast arrays of air showers and neutrino detectors aim to achieve a clearer understanding of these cosmic rays, which could ultimately unlock the mysteries of extreme astrophysical processes in the universe. The answers to these questions can help deepen our understanding of the fundamental physics and nature of the cosmos on the largest scales. Type Ia supernovae are a spectacular and predictable type of explosion, often used by astronomers as cosmic yardsticks to measure distances in the universe. The origin of these events can be traced to the example of white dwarfs, which are the remnants of stars that have exhausted their nuclear fuel. A white dwarf is composed mostly of carbon and oxygen, and it is kept from gravitational collapse by electron degeneracy pressure. For a white dwarf to ignite in a Type Ia supernova, it must undergo a process called accretion, during which it gains mass from a companion star in a binary system. This companion could be either another ordinary star or another white dwarf. As a white dwarf accumulates matter, particularly hydrogen and helium, its mass gradually increases. According to an established threshold known as the Chandrasekhar limit, when the mass of a white dwarf approaches about 1.4 times the mass of the Sun, the temperature and pressure in its core become high enough to initiate nuclear fusion. Once fusion begins, it triggers a rapid, uncontrolled process that converts carbon and oxygen into heavier elements. This reaction releases a huge amount of energy, and the white dwarf explodes in a violent flash. The explosion is not a typical stellar detonation. Instead, thermonuclear acceleration occurs. This means that thermonuclear reactions proceed at an accelerated rate on the chain reaction principle, resulting in a cataclysmic release of energy that completely destroys the white dwarf and produces huge amounts of radioactive material. The aftermath of a Type Ia supernova causes the heavy elements to disperse into space, enriching the surrounding interstellar medium. These elements contribute to the formation of new stars, planets, and eventually life itself. The predictable luminosity of Type Ia supernovae, due to the constant mass of the exploding white dwarfs, allows astronomers to use them to measure cosmic distances and study the expansion of the universe. Understanding this process deepens our understanding of stellar evolution and the life cycle of matter in the cosmos.